Section 3, which is mashing home runs at the Little League World Series. So when I was little, I wished I could play at the Little League World Series in Williamsport, Pennsylvania, but it didn't happen. Polymer physicist. But as a polymer physicist, I can make dreams come true for future Little Leaguers with my new bamboo carbon nanotube composite. So carbon nanotubes have this Young modulus of 950 gigapascals. Bamboo, 25 gigapascals. Composite will be a 90-10 mixture. Sent my design to the manufacturer, but unbelievably sent me a bat that looks like this, where my fibers are oriented at this kind of random 28-degree angle. So I know that the Young's modulus of my fiber is going to be my carbon nanotubes, which is going to be 950 10 to the 9th times 10 to the 9th. My Young's modulus of my matrix is going to be 25, my bamboo, times 10 to the 9th. And fraction of the fiber is going to be equal to 0.1. Fraction of the matrix is going to be equal to 0.9. Let's make that 0 to look nice. I can also, from that, already start to calculate my Young's modulus. I'm going to call it just 1 in the direction of the fiber is going to be EF times FF plus EM times FM. And E2, the direction, again, transverse to the fiber is just going to be 1 divided by F divided by FF divided by EF plus FM divided by EM here. And let's go ahead and just make sure those values are correct. Let's go ahead and look at E1, E2. And again, we could see stiffer in the direction pulling along the direction of fibers than in the transverse direction. Excellent. So let's go ahead and see what this problem is actually asking us. How should the carbon nanotubes be aligned so I can mash home runs, draw schematically? Well, ideally, I'd want those, my nanotubes to be just like this, because I want the baseball to come into here, and then I want to, again, the stiffer the material, I want my bat to be as stiff as possible, so I want to hit that ball, and the stiffest direction is when I'm aligned with the fibers. Excellent. So undergraduates didn't know this was the case, so they measured the stresses and basically in this coordinate system here, in this 1-2 direction. So in this coordinate system with these fibers aligned like this, they didn't know that, so they just stressed my material. So we obtained these values. So this is kind of in the what I'm going to call the new coordinate system. So new coordinate, because this is again rotated from our original coordinate system. This E1 and E2, actually let's go ahead and write out the S matrix. S divided by E1 minus new 2-1 divided by E2. Oops, excuse me. I believe this is correct. Let's go ahead, we'll double check this. I'm going off of pure memory. Minus new 1-2 divided by E1, 1 divided by E2, 0, and 0, 0. This is a good one to have in your Mathematica notebook, ready for the exam. Here, this is my S, my compliance matrix, tensor. Let's go ahead and look right here. Make sure that we're all correct. Everything's copacetic. So E1 minus new 2 E1, E2, there we go. And that's it. So I have some unknowns in here. We'll figure that out. But this is the stress tensor, again, aligned with these, in the original coordinate system, or aligned like we've kind of drawn it here. So actually, let's go ahead and look at this. Oops. Let's look at our practice exam. So if they're aligned in this direction, actually, I'm going to read my coordinate system like this. So if we're aligned in this direction, we could use this compliance matrix. But the 2 direction, that'd be kind of the, again, transverse direction. But instead, we're in this new coordinate system where we're rotated this theta of equal to 28 degrees. So these are the strains and stresses associated with that new rotated coordinate system. So I'm going to say new stress is going to be equal to, I'm going to say, so 10 times 10 to the 6. So I'm going to call this my sigma 1 p. I'm going to call it my prime. So 10 to the 6, sig 2 2p equals 58 times 10 to the 6. Sig 1 2p equals 100 times 10 to the 6. My E1 1p, then prime direction, 0.00. Let's see, is it 3 zeros? 0.0123677, and then I know that my E22P is going to be equal to minus 0.0034, and my gamma 12 P is going to be equal to 0.00476. All right, so my new stress are all these, so my new stress is going to be sig11P, sig22P, sig12P, and my new strain is going to be equal to E11P, E22P, and then gamma 2P. All right, so let's see what the question is actually asking us to solve for. So we need to figure out and determine the rotation to get the principal stress state for the 1-2 plane for the fibers oriented at the angle given from the manufacturer. Well, if I want to figure out the rotation of principal stresses, I know I could just do T dot my, so let's define my T up here. Here, this will be useful. So all I'm going to do is do my new stress, actually T dot new stress, and then slash dot. I need to solve for when this, specifically the third component, set is equal to 0, and then what is the value of theta? Let's do numerical solve. So those will be kind of my rotations. And again, you could multiply this out and get kind of some of these values. So that's going to be the rotation to get the principal stress state for that original, or for the new, essentially what we're calling that new angle. So when our fibers are kind of stressed, or like this orientation away from that, the orientation 28 away from that kind of principal angle. Now it's asking us to write out the compliance matrix quantitatively for the coordinate system where we can mash our home runs. So we need to figure out what is our compliance matrix numerically. And we could kind of solve for these three unknowns using the following equation, remembering all the way back into kind of our lecture notes here. So we have this expression for what's the strains and the stresses in our new coordinate system, and how we could relate those here. So all we're going to do is, let's go ahead and write, let's look at S here. So that's S, so we have three unknowns, and really we actually have some equations that can kind of give us that relationship as well. So let's go ahead and solve for that. So let's say that our new solve for new strain, set that equal to R dot T dot inverse of R dot S dot inverse of T, and then dot my new stress. And then I want to solve, actually, I can just leave that here. I want to solve for when, what is our new 1-2, new 2-1, G12, right here. Actually, let's do ahead and do numerical, actually, and then we need to do slash dot theta goes to 28 degrees. And we could see basically some values right here. So let's go ahead and actually, let's make sure, we might have to add an additional expression here. So new 1-2 equals this, new 2-1 equals this. Let's say new 2 divided by, because if we look up here, new 2-1 divided by E2, and new 1-2 divided by 1. We have three unknowns, so all we're going to do is use the expression that we've kind of been utilizing previously. So let's go to our lecture notes right here. Let's go up a little bit right here. We have our stresses, our new strains where you have our new stresses. So let's go ahead and solve this equation. So I want to solve for new 2-1, new 1-2, G12 in terms of my new strain. Set that equal to R dot T dot inverse of R dot S dot inverse of T, oops, and then dot new stresses, or new stress. I want to have all of this at our angle of rotation, which was theta goes to 28, And let's solve for new 1, 2, or new 2, 1, new 1, 2, G1, 2. And we get our values. Now you'll notice that some of these values look a little bit strange, specifically new 2, 1. And also, there's kind of a mistake, an error in this example problem. You'll notice that our relationship, this is not a symmetric matrix. So you kind of point out that error in the solution. So if you look back, and actually we could show it right here, new 2, 1 divided by E1, new 1, 2 divided by E2 are definitely not the same. They're pretty close, but actually it's the opposite. New 1, 2, E1, new 2, 1, E2. Let's go ahead and show this. Those are not exactly, they're not the same. So there's a mistake essentially in this kind of a mathematical description. But again, this is just an error in kind of the math. The procedure is the exact same way, but you can kind of notice this and then stop the problem at this point. But let's continue it just for fun's sake for this exam. So that's rotation. We've done this rotation. We've written out the complex matrix quantitatively for the coordinate system where we can mash home runs. And now we want to calculate the strain for the coordinate system where we are mashing home runs. So really what we're just looking for is our original values. So we can actually calculate that, again, fairly straightforward. So what is it going to be? Well, if we want to calculate our original coordinate system, we can just solve. So let's go ahead and back calculate. Let's go ahead. So let's utilize this expression again here. So if I want to find the stresses in my old coordinate system, I could just do this. So these are my stresses in the new coordinate system. So I could do the inverse. I could do inverse of t dot new stress. And then I could basically rotate them at that angle. So inverse dot t slash dot theta goes to 28. Let's look at that numerically. And let's compare that to my new stress here. So again, those are the systems in the old, or actually in the new coordinate system. These would be the stresses in the old coordinate system. And we can do the same thing for strain as well. So new strain, you can just kind of see the procedure to do that right here. So I would just do actually, I can make my new strain a little bit simpler. So this would be my old stress. So old stress is equal to this. And so we're going to do something very similar actually by basically using the solve. So if I want to solve and say that the new stress, I could do it in the inverse method. New stress set equal to t dot basically sig1 OG, sig22 OG, sig12 OG slash dot theta goes to 28. And I could kind of solve for what is my sig11 OG, sig22 OG, sig12 OG. And then get these values right here. And let's numerically solve this. And you can kind of see, look at these values, exactly the same. Great. I can do something very similar for strain as well. So let's solve it first using this kind of solve method. So I want to do in solve, I want to figure out, okay, I have my new strain, which is going to be set equal to r dot t dot inverse of r dot my, let's see, E11 OG, E22 OG, E1 or gamma 12 OG. Let's set that equal slash dot when theta goes to 28, and I want to solve for E11 OG, E22 OG, and gamma 12 OG. So I solve for those values. I get these expressions right here. I could also kind of just look at this and do that kind of linear algebra. So I could take my, I need to do my inverse of r. I'm going to dot that with my new strain. And then I need to, basically that's going to convert that. I need to do my t, because I need to rotate that kind of coordinate system there. and then I need to do actually 2, and then R to convert it back, and then actually I might need to do an inverse T, excuse me, inverse T because we're rotating the opposite direction, and then this is all when slash dot data goes to 28. And you can see I get the exact same values. Perfect. So multiple ways to skin a cat, and you can kind of, again, double check your answers. That's what the nice part about these problems are. So next time we're going to get into our last example problem, which is dynamic mechanical testing, and we'll see more qualitative. All right, I'll see you on the next video. Thanks. Bye.